For AP Problem 10, it says a student prepares 100 milliliters of a saturated solution of MgF2 by adding 0.5 grams of solid MgF2 to 100 milliliters of distilled water at 25 degrees Celsius and stirring until no more solid dissolves. Assume that the volume of the undissolved MgF2 is negligibly small. The saturated solution is analyzed, and it is determined that the concentration of F- in the solution is 2.4 times 10 to the negative third molarity. For part A, section 1, it asks, write the chemical equation for the dissolving of solid MgF2 in water. So we can just disregard water because it doesn't affect it. So we have MgF2, which is a solid, and that disassociates into Mg with a plus 2 charge plus 2 F minus, because there's 2 over here. For section 2 of part A, we're asked to calculate the number of moles of MgF2 that's dissolved. So to do that, we take 2.4 times 10 to the negative 3 moles of F minus, divide that by the volume, which is 1 liter, then multiply by 1.1 liters, and then we multiply that whole thing by the by 1 mole of MgF2 that over 2 moles of F minus. So that'll give us this right here. And then we multiply those two together, and that'll give us 1.2 times 10 to the negative 4th moles of MgF2. For part 3 of part A, we're asked to determine the value of the solubility product constant KSP for MgF2 at 25 degrees Celsius. So we have Mg plus 2 right here, the concentration, is equal to half of the concentration of F minus. So the concentration of F minus is 2.4 times 10 to the negative 3 molarity. And we divide that by 2, and that'll give us 1.2 times 10 to the negative 3. And we plug that into our KSP value, our KSP equation. That'll give us 6.9 times 10 to the negative 9. For part B, it says a beaker contains 500 milliliters of a solution in which both Ca plus 2 and Ba plus 2 are present at a concentration of 0.10 molarity at 25 degrees Celsius. A student intends to separate the ions by adding 0.20 molarity NaF solution, 1 drop at a time, from a burette. At 25 degrees Celsius, the value of the KSP for CaF2 is 3.5 times 10 to the negative 11th. The value of KSP for BAF is 1.8 times 10 to the negative 6th. For part 1, it asks which salt will precipitate first, CaF or BAF, to justify our answer. For part 1, I said CaF because it has a smaller KSP value, and since the number of ions are the same, it'll only depend on the KSP value, and that being CaF2 is smaller. For the next part 2 and 3, it says for parts 2 and 3 below, assume that the addition of the NaF solution does not significantly affect the total volume of the liquid in the beaker. Part 2 asks, calculate the minimum concentration of F necessary to initiate precipitation of the salt selected in part 1. So for part 2, I said the KSP is equal to 3.5 times 10 to the negative 11th, which is equal to 0.10 times the molarity of F minus squared, or the concentration of F minus squared. So we would divide 0.10 from 3.5 times 10 to the negative 11th, and that'll give us the concentration of F minus squared is equivalent to 3.5 times 10 to the negative 10th. Now we would square root both sides, and the concentration of F minus would be equal to 1.9 times 10 to the negative 5th molarity. So part 3 asks, calculate the minimum volume of 0.20 molarity NaF that must be added to the beaker to initiate precipitation of the salt selected for part 1. So for part 3 I said we will have 500 milliliters of our precipitate if we assume that we can ignore the NaF. So for part C, it says there are several ways to dissolve salts that have a limited solubility, and it asks us to describe one procedure to redissolve the precipitated form in part B. So for part C I said anything that is done to shift the equilibrium to the product side is okay. So adding H plus ions and increasing the temperature would all work for that.